welcome to lecture 21. So, last time we looked at various storage allocation strategies for simple data. So, let me just briefly summarize that. Firstly, we had constants. I said that there were lots of important questions of policy that one should answer before it gets down to the implementation. Should you allow structured constants? Should you allow simple constants? What happens if you take various decisions concerning these? Should you allow, should you insist on a compile time evaluation of a constant value? Should it be done at runtime? If so, should you do it just before program execution, or should you allow it to be more flexible and each time the block is entered? In which case, each time the block is entered, it's a constant only for its particular lifetime and not a constant for the entire program. So, should constants be allowed? Should constants just be names of some literals, or should they be allowed expression values? And then if you allow expression values, then would you insist on a compile time evaluation or a runtime evaluation? If it is a runtime evaluation, would it be just before program execution begins or each time the block is entered in which the constant is declared? Then as far as variables are concerned, should you allow initialization? Should you insist on initialization always? What happens to initialization of large structured variables? What kinds of languages allow what kinds of initialization for variables? And finally, we also classified variables in various kinds, those which are automatic in the sense that they are created at block entry and are destroyed at block exit, the own variables or the static variables which are created during program entry, which are created at the entry to the main program, and they have a lifetime extending right through the execution of the main program. The area in which it would be most natural to allocate these variables, and then of course there are programmer controlled variables which are usually explicitly programmer controlled, and they are usually allocated on heap. So, they have a lifetime which is different from their scope in the sense that they are explicitly created or destroyed by the programmer. Right. So, today we will look at structured data in some greater detail. So, whatever we said previously holds for let us say simple variables, simple constants and so on, which means when I talk about simple variables or simple constants, what I mean is that the underlying virtual machine already supports those types as data types. So, there are predefined operations, predefined sets of values, and of course, then we are talking so they are simple in that respect. If you had an underlying virtual machine which only dealt with matrices, then that would be a simple data type for that machine, right. But in general, in most general purpose languages, the simple data type usually are scalars of the form integers or reals, constant, strings, booleans and so on. So, now we are talking of structuring data, simple data into more compound data. So, it means that you have to somehow combine simpler pieces of data, scalar data in the view of the virtual machine on which you are implementing, into compound units to be regarded as a single data item. So, in any kind of structuring operation, there are what are known as constructors and what I have called, but which no other programming language text calls, deconstructors. So, when you put together pieces of data and structure them into large units, then you also require methods of exploding that large unit and obtaining the simpler components. So, this I am calling them deconstructors, but in the case of particular structuring operations they have particular names, right. So, I would I would not call it destructor because that means completely destroying the data, but deconstructor is that you split it up into its components again. So, you take some simpler pieces of data, combine them together, but later you might want to access those individual components for some reason, maybe to construct new structured data. And so, you would like to deconstruct a compound unit into its individual components, right. So, most we should look at structuring data in terms of the underlying what are the most common structuring mechanisms that mathematics provides, and how does one model those structuring concepts in our programming. So, let us start with the simplest possible structuring mechanism in mathematics, and that is a tuple, right. So, the constructor in this case is just a Cartesian product, right. So, you can take Cartesian products of two sets, for example, and you get ordered pairs. You get n tuples by taking Cartesian products, an n-fold Cartesian product of n sets, and you get n tuples of this form. And given any tuple, what you require are corresponding projection functions, right. So, given a tuple, the ith component of that tuple should be extractable. Remember that all these individual sets may be of different types, I mean they may all be really different sets. So, what you are looking for are forms of projections, projection functions. Projection functions are the deconstructors for a Cartesian product. Yeah. So, please note that deconstructor is really my name, I mean it really is not available in anybody in any other programming language text, and deconstructor is actually a philosophical word dealing with some modern concepts in linguistic philosophy, but anyway I think it is a good name to coin. So, we will use it for this purpose. So, projection functions are the most common are what you require for exploding a Cartesian product and extracting individual components. And so, now let us look at how these constructors and deconstructors are provided in some languages. So, in most languages, in most imperative languages, you have records with named fields as the only tuple formation construct. Okay. And the fact that you have got named fields means that you use a field selection operation which uses the name. So, field selection a field selection in a record is the major operation to explode or to extract an individual component of a record. In ML, of course, what they have is there is an explicit tuple construction mechanism and an explicit deconstruction which you can which is through a pattern matching rule. Yeah. So, since ML is quite clear about the kinds of patterns the tuple must possess, what you have is you could have a typical you could go through a typical session, an ML session like this, in which you construct a tuple A which has these values, and the ML type inferencing mechanism automatically gives this a type which is defined by this Cartesian product. I mean, of course, the individual patterns actually make it clear what what constitute what is the construction operation, what is the what Cartesian product, what domains are involved in the Cartesian product and in what order. And the most common way of deconstructing is to give a declaration like this, and that, I mean, note that B, C and D are names which are not pre-declared. I mean, which is not, it is not that, well, it is not that while constructing this tuple you gave these field names. These field names are absolutely new, but the pattern matching facility of ML clearly indicates that if there is some new name and you are declaring this in this fashion, then you have to do an appropriate mapping of these what might be what are ML variables to their appropriate values. So, you should get a response which actually is something like this. And so, the deconstruction is done through very often through pure pattern matching, and this is not true just of the tuples, but it is true of any data type in ML, that you can actually do any kind of, for any kind of structured data in ML you can actually do deconstruction through such a pattern matching mechanism. So, whether they are ML records or records of records to any depth, records of tuples of lists and so on and so forth, you can do deconstruction just by using the pattern matching facility, right. So, in various most other languages, while ML has taken a very strict mathematical view towards data types, the constructions are such that they model an elementary mathematical text. I mean, what kinds of constructions and deconstruction mechanisms should be provided and how should they be how should they be implemented. Whereas, most languages were actually did not have not considered this this problem of providing a separate construction or deconstruction mechanism for many mathematical operations. They have usually confused the abstract operation with a representational equality. For example, the Pascal record is one such case. It's is one thing, but most commonly are these are the kinds of mechanisms used in Lisp and Scheme. The Cartesian product is clearly a different operation from a list forming operation, from a sequence forming operation. The fact that Cartesian products are isomorphic to certain subsets of list formation is a different matter altogether, but it is fundamentally a different operation. Whereas, most of these the older functional languages, mainly Lisp and Scheme, which is of course just a daughter of Lisp with a simpler structure, only use lists as list construction as the main operation and the list operations themselves as the deconstructors. So, so an ordered pair in Lisp or Scheme is no different from a list of 2 elements. An ordered triplet is no different from a list of 3 elements. Okay. Whereas, logically they are two different things. I mean, a list is meant to model a sequence and not a tuple. So, however, since they are isomorphic, since lists are a more powerful construction operation, it is assumed that you can somehow, since you can program tuples and so on through lists, it is assumed that it is not necessary to have a fresh data type called lists, called tuples. So, in fact, most of these languages actually do this. I mean, whatever they have in the past, they have confused what constitutes an abstract construction or a deconstruction operation from the fact that it is easily implementable. I mean, they have confused these two issues. Okay. So, the other important operation is what might be called the sum or disjoint union, or it is also called a coproduct. The Cartesian product is a product, and this is a coproduct, well, in some category of domains, but let us not worry about that. So, it is what I might call a sum. So, you have the sum of two sets, and what I said loosely was that this is really like maintaining the identities of the elements in the individual sets. These two sets may not be disjoint, but you have to somehow maintain the identities of the elements drawn from these two sets. And so, the natural thing to do is to have a tag or a discriminant which will clearly give an identity to the elements in this union. Okay. So, when we are talking about a sum or a disjoint union, we are really talking about two injection functions which are of this form. There is an injection function in1 which takes an element from A and gives you an element of A plus B, and there is an injection function in2 which takes an element from B and gives you an element of A plus B, right. So, actually these two injection functions are really what constitute the constructors for the disjoint union operation, and but most and so if you look at it as a construction which is obtained through injection functions, it is not necessarily the same as having a tag or a color to distinguish between the elements. I mean, this is only a representational mechanism, it is not a logical mechanism. The logical operation is just A plus B. So, I have used this to indicate that in my past lectures, whenever I use the disjoint union, I may have used an equality, but here what I am saying is it is not really an equality, it is an isomorphism, okay, which means that the two sides are not exactly identical. There is some logical information in this plus which is made explicit through a tag or a discriminant, and this is really representational rather than being logical. Yeah. So, however, what has happened is that just as in my past lectures I actually identified this with this, most languages have also identified these two, and they use a tag in some form or the other, right. So, most languages actually have records with variants, with variant fields, and what you do is you have to in order to identify individual fields, or rather to take the identity of the individual elements in this coproduct A plus B, they use this tag and the operations that come with it, that come with the appropriate tag. So, you do a case analysis on the variant. So, for example, so this is the most common thing that has been used in all languages starting after Algol 60. So, PL1 for example was COBOL has a struct mechanism which is similar to the records of Pascal, but the variant mechanism really comes from probably the first language to use it is PL1, and then Algol 68 and then Pascal and so on and so forth. So, most languages actually have a form of records with variants as and the variant field is the tag, or a tag field is used to disambiguate, to provide an identity for where a certain element comes from, right. So, however, the problem is that the variant records, for example, let us look at the Pascal variant records. There is a certain problem, a certain insecurity which actually was exploited even by Nicholas Wirth in his own original compiler own original Pascal compiler. So, But however, the construct, even though it was very useful for his compiler, the construct came under tremendous criticism because of this reason. So, I can have a record declaration like this. Normally, I mean, very often what you are doing is this variant is often a part of a larger record declaration, which means that you are taking some Cartesian products initially, and then you are taking a disjoint union of two different kinds of Cartesian products, right. So, that is really how you should look at it, but let us look at it and look at the variant in isolation. So, there is a tag field which maybe is a Boolean, and if the tag is true, then it is what it has is an underlying integer, and false is if the tag is false, then it is character. So, what you are taking is, in this particular declaration, you are just taking a disjoint sum of integers and characters, right. This, of course, what is there within this parenthesis could be more complicated. I mean, it could be another Cartesian product or some such thing. But so now what you can do is, now this declaration is a variable, and therefore it is, and since it is a record and you use field selection, what you can do is, the normal idea of designing such a record is that you do a case analysis on the tag and do appropriate operations, maybe integer operations or character operations. Remember that when you take a disjoint union of two sets, the injection function is such that, the injection functions are such that once the identity of the individual components of a set are known, the operations of that data type become applicable. I mean, you import also the operations of that data type. So, for example, if you are taking the disjoint union of integers and characters, and you know that there is an element which actually came from the integers, then you could do, for example, addition, subtraction. I mean, you could take two different records which both belong to whose parent in the parent component is integer, and you could add those values. If they are characters, I mean, for example, you could look at you could do something like, you could compare the two characters, or take some successor of the character, whatever, predecessor, whatever. But the point is that if you have two different records P and Q with the same declaration, and one has a tag which is true and the other has a tag which is false, then theoretically, for example, you cannot add the integer component of one to the character component of the other. I mean, the operations remain distinct, right. However, what happens is that since the record is just a variable and its individual components, its individual fields are also just variables, what one could do is, one could actually assign the tag a value like this, and then one could change the value of the tag, and then look at an operation from the other data type, right. So, you started off with P being from the characters and you assigned it a character, and then you change the tag so that now P became part of the integers, and so now you can write out an integer value. So, this is something that if done this is something that leads to, for example, type and runtime insecurities. Certain as the pride of a Pascal implementation is that every type is compile time determinable. Now, with the variant records, you have something that is not compile time determinable, that is not even really runtime dependable, and so in the sense that you cannot introduce checks, you cannot introduce runtime checks, because you do not know how the tag is going to vary. After all, I could change this to some complicated Boolean expression. So, it has a type which, it has a schizophrenic type which keeps changing depending on the actual value does not change of the individual components, but there is a side effect on the type of the individual component by changing the value of the tag field, right. So, this is the reason this construct came under severe criticism, because it leads to firstly an abuse of the type structure of the language, and then it makes runtime checking, type checking really impossible. After all, there are other ways of doing the same thing, and they should be used, and you should not be able to abuse the flexibility that is provided, right. So, what happens? So what happened was that many languages actually avoided this problem in various ways. So one is the language of Euclid. Let me first say that I will always use Pascal or ML type syntax, and I do not swear by that syntax. I do not know the syntax of Euclid or of the many other languages that I would be discussing. So, what I will write them is in a sort of Pascal like fashion. The whole idea is that you should worry about the semantics rather than the syntax. So this syntax is definitely not Euclid compilable. So, what I have used is a Pascal like syntax here. So, now what Euclid did was that one thing that you could have done in that Pascal declaration is actually define that record, variant record, as a separate type, and then define and then declare that variable p as being of that type. So, you can give that type a name and then declare that variable p is of that type. That is something that could have been done, but the point is that that does not solve the problem of those runtime insecurities, right. So, what Euclid did was that it actually parameterized the tag in the declaration itself. So, if you declared some variable to be of this type, then since this is a variant record type, you had to give an initialization for that tag, and a compile time check was introduced to ensure that there was no way that the tag was changed in the program. So, the identity of the disjoint union was preserved by putting an initialization for the tag field in the declaration of a variable itself. So, you could not mix two variables very easily, right. So, you could, however, so you could define two different variables of the form p and q like this. So, note that, so p comes from the integer component of the disjoint union and q comes from the character component of the disjoint union. So, the properties of the injection function are rigidly maintained, but you could also, very often you require temporary variables. So, then you could also declare something like this. So, you could declare some variable like r, in which there was a new reserved word called any, and what it meant was that you could assign any type to this. So, the natural question is, so could you have, for example, so can I do this? Can I first, in the main program, can I assign a value to p, assign that p to r, and assign that r to q? Thereby I would have again violated that, I would have moved from one component of the disjoint union to the other. So, what Euclid did was it banned all forms of such assignments. So, if you are going to use r as a temporary variable, you could assign p to r, but you could never assign r to q. Okay. So, however, you could assign, once r has been declared to be of the same type as p, you could assign r to some other variable, let us say s, which is of the same type as p. Okay. So, there is a runtime type checking. So, based on the tag value you could do appropriate assignments. So, if this portion were inside a loop, then occasionally, depending on the value of the variables that you are using, r might be either of the type integer or it might be of the type character, and you could do a case analysis, but you could never make such an assignment. So, this is, so in this case, so note that in some sense this R is of a type, is of a super type compared to either of the individuals P or Q. So, by assigning P to R, you are widening the type, assigning P which is of a narrower type to a wider type, to a variable of a wider type. So, that is called widening. You could do widening, but you could not do narrowing, which means taking a value of the super type and assigning it to a narrower type. You could not do this arbitrarily unless you actually did some, I mean it was very difficult to do this. So, you had to, so there were some predefined types, but what it means, it also complicates matters a lot when you want to actually do explicit type coercion. Yeah. So, but their single purpose in life was to avoid the pitfalls of the variant records in Pascal, and so they took this view. The language Algol 68 actually took a more pragmatic view. Firstly, this is probably the first time I am mentioning Algol 68. Let me first mention that Algol 68 has got no relation whatsoever to Algol 60. I mean, it's not like Fortran 4, Fortran 77, Fortran 90. No, it's not like that. Algol 68 is a completely new language, which the main purpose, the main design issues in Algol 68 were to not only specify, Algol 60 was the first language which used a BNF notation to specify syntax, the context free syntax, and the idea in Algol 68 was not only you should specify context free syntax, you should also specify context sensitive syntax. So, they had grammar rules which were so complicated that I doubt if anybody other than the language designers have actually written substantial programs in this language. So, but Algol 68 had a very interesting method, which was just that they actually gave a union of types in this fashion. So, you could actually define a union like this and do a case analysis. There was no tag field, and therefore there was no possibility of abusing the tag field, right. So, you could look at any particular variable of this coproduct type and you could do a case analysis based on whether it comes from here or it comes from there. So, there was absolutely no tag field, and therefore, there were no tag field assignments, there was no way you could change those tag field assignments, there was no question of widening or narrowing, and they thought they had put everything in watertight compartments, things could be compile time checked, and but you could do assignments. You could do assignments between various variables of the type int char, and but along with that information, that is the actual value of the assignment, the parent type which came from the injection function was also carried through. So, you had to always do a case analysis on finding what was the injection function used in order to do whatever manipulations you want, right. So, more modern languages like Ada for some reason just used exactly what Pascal has done, in spite of knowing about all the insecurities of the Pascal variant record, right. So, the only difference was that Ada gave it a 4-syllable name called a discriminant, and which sounds more grandiose, and but what they did in order to avoid the insecurities was that they said that anytime you are trying to change the tag field, you cannot selectively update the tag field. What you have to do is you have to change the entire record, you have to reassign the entire record. So, this way they allowed for a flexible coercion of types, but then that coercion included that cohesion meant that the programmer, by having to change the entire record including the tag, knew exactly what he was doing. So, so you first change, so you do the entire thing in a block, the changing of the entire record either in a block, but since Ada also allowed various kinds of compound initializations, since Ada allowed mechanisms, even syntactical mechanisms for doing initializations of aggregate objects or compound objects, you could do the entire thing also in a single command. You could change the entire record in a single command through various syntactic means by the use of various kinds of brackets. So, if you had records within a record, so the components of a record would be written in parentheses, very much like the ML tuples, and if there were records within records, then you would have more and more parentheses, nested parentheses inside. And so, a large record could be changed in a single assignment command by using an aggregate. So, the large record including the tag could be changed by in a single command by using an appropriate aggregate, but then that only means that only meant that the programmer knew explicitly that he was changing the tag field, and he was doing the change in the tag field at the same time that he was changing the other components. They are not being done in a selective or distributed fashion. I mean, it is the code for changing the tag field and changing other areas of the record were not distributed along the in various places within the program. I mean, it was all done in one single command. So, it localized the problem of the variant record problem of Pascal. So, which they found was the most acceptable to them. There is a coproduct construct also in ML, but that is at the level of data types. So, what a typical ML coproduct would look like is that if you look at our disjoint union, it is not just the sum of two sets, it is actually a sum of two different data types. So, if you have integers and characters, and if you are taking the disjoint union of integers and characters, then you are also importing for the appropriate components the appropriate operations available with integers or the appropriate operations with characters. So, you are actually defining not just a new set, but a new set with a new set of operations where each operation comes from either of the two injection functions, right. So, what it means is that, so if you look at if you look at the operations of if you look at this construction of an int car data type, it is not just a construction of a new set, but it also has summation, multiplication and so on and so forth, ordinal numbers of characters, getting a character from an integer, and it has all these operations, except that all these operations are conditional, they are undefined. So, for example, ordinal number of an integer or rather obtaining a or adding two integers is not available in the character domain. So, it is conditional, and so what you are actually doing is you are defining a new data type of this form. So, by a data type we mean a set equipped with its operations. So, an integer is not just a set, the integers are not just a set, but they are a data type which have associated operations with them. So, you could define a data type like this. My ML syntax is also quite informal, so I do not guarantee that all this is compilable. So, you actually define the injection functions in ML. So, you would actually define something like in1 of int, in2 of car, right, and each time you would carry this injection function itself as the tag for each element, right. And so, what you would do is you would always, whenever you are assigning a value to this data type, you would actually write something like this: in1 space 5, let us say, right. So, this clearly specifies. So, the injection function itself acts as a tag and they have two distinct tags. It solves that problem of, I mean, of course, since it is a functional language, of course, everything has a constant value. So, you actually have two different tags for this data type. If you did an n-fold summation, you had n different data types, because the injection functions were always tagged on as patterns with the component, and the injection functions ensured that you had type compatibility whenever you performed operations, whatever. So, you could not do strange coercions unless you were explicitly conscious of it, unless you took into some character, unless you took its ordinal value, you could not treat it as an integer, right. So, ML actually follows the mathematical definition of a coproduct or a summation in a very strict fashion. Yeah. So, lastly we have to look at the storage allocation issues, and of course, there is also this thing that given an arbitrary variable of this type, you could do a case analysis just as. So, if you could have a function some f, okay, applied to p, which would actually be defined by you could actually define it as f of in 1 some x equals something f of into some y equals something. So, you could do the case analysis, the standard case analysis that is available in ML through the pattern matching mechanism is also available to do case analysis for an arbitrary variable of this summation type, right. So, so finally we have to look at storage allocation issues. So, what do? We just, when you look at variant records, so let us first look at ordinary records without variants. By records, of course, here I do not mean ML records, but in general Pascal like records or PL1 COBOL like structures. Okay, so you could have something like this, and what you do is you just allocate you know how much space you require for each of these components. So, you allocate a contiguous block of memory equivalent to the sum of the spaces required for each of these at runtime, right. So, all that you do is you just allocate it all contiguously, and you do not require, and part of the so you just place the individual fields in contiguous locations, and in the order of appearance in the record declaration, which also brings in another type issue which we will come to later, another of those various insecurities in these imperative languages which have records. So, one thing is that you do not really, if you do this, then you do not really require any runtime descriptor. Anyway, if it is a variant record in Pascal, then you do not really know what kind of runtime descriptor you can keep for it. So, and the address of any particular field which you require for deconstruction is just some offset plus the sum of the sizes of the individual fields up to that, and since the order of appearance in the declaration is important, that is the order in which they are also stored. So, you can just take the size of individual fields and contiguously allocate it, and you can randomly access an individual field of a record by a simple runtime calculation, in fact by a simple compile time calculation, right. The offset is the only thing that is going to be known at runtime. Part of the offset consists of a relative start of the block in that runtime stack. The other is the absolute portion of where that block is going to start in the runtime environment. and that depends on its lifetime, right. So, it depends on the number of procedure calls, maybe number of blocks under it and so on and so forth. So, the offset consists of an absolute component which is not known except at runtime, and a fixed relative component which is known at compile time. So, that and the sizes of each of these fields is known at compile time. So, this calculation of the fixed offset from the current base of activation record to the appropriate field is all compile time calculatable, is all compile time determinable. And so, so you can do random access quite easily with such a structure. Of course, what might happen is, since a record is a structured data type using individual components, you might require some runtime descriptors in order to do various kinds of checkings. After all, for example, you might have a record whose one component is an array with certain fixed bounds, then you have to ensure that the array index does not go out of bounds and so on and so forth. So, the runtime descriptors are usually necessary for arrays, right. We will come to that when we do arrays next time. So, but for the record as a whole, you are not going to have any runtime descriptors. You are just going to have runtime descriptors as appropriate for the individual components, right. And in the case of a variant record, you really have nothing to do except to allocate some maximum value computed over all possible variants of the record. So, you just look at all possible variants of the record, find out which one requires the maximum amount of storage. The fixed part of the record anyway is going to use only that much. That is one of the reasons why Pascal insists that the tag field and the variant component should always be the last declaration in a record if it is present. So, that the fixed parts of the record anyway have fixed memory allocation, and the variant part could have variable amounts of memory allocation, but normally most Pascal implementations would just take the view that we will just take the maximum over all the possible variants that you have and just allocate that much space. And if you are looking at a smaller variant, then that just occupies a space that is a part of this larger space that you have allocated, and the initial portion of that larger space is all that it will occupy, right. So, that is how these record structures are implemented, and that is how they allow also random access to the fields of the record. So, next time we will do arrays and some other data types, and then we will get on to control structures. Thank you.